today we will continue with our topic series. Okay. So today's first point is the theorem Cauchy Convergence Criteria for the convergence of series. Okay. Now we have already seen the criteria Cauchy Convergence Criteria for the convergence of sequence. Okay. And this is very much similar to that criteria. And I have already told you that if you do the topic of sequences very properly, then you will find this topic in series very much easy. Okay, because the series has a link or connection with sequences. Okay, because we know a series is convergent if only sequence of partial sum is convergent. So sequence comes into that point. Okay, so sequence, we have to do sequence properly. So the criteria is the series Xn is convergent if only for every epsilon greater than 0 we can find natural number such that whenever m and n are greater or equal to that natural number m, the mod of xn plus 1 plus xn plus 2 up to xm is less than epsilon. Okay. So we will prove this theorem. Okay. So proof is not very hard, it is very easy. So let series Xn is convergent. Now we know a series is convergent if and only if the series is convergent if and only the sequence Sn, okay, of partial sum. And what is the sequence of partial sum? It is the sum of first n element of the series. So the sequence Sn is equal to x1 plus x2 up to xn. This is the n term of that sequence. Okay. So the sequence of partial sum is convergent. Okay. The series is convergent if only its sequence of partial sum is convergent. The sequence Sn of partial sums is convergent. So now here the sequence whose n term is this is convergent. Okay, this is if only our sequence Sn is whose n term is given is convergent. Okay, but we know the Cauchy criterion. A sequence is convergent if only it is a Cauchy sequence. Okay, so this happens if only Sn is a Cauchy sequence. Cauchy sequence. Okay. Now, since Sn is Cauchy sequence, we know the definition of Cauchy sequence. So this happens if only for any epsilon greater than 0, there is this natural number m depend on epsilon such that whenever m and n greater or equal to that natural number m, difference between Sm and Sn is less than. Okay. Now, since m and n are some real numbers, okay, we will assume that one of the two is greater than other. Okay, so you will take the condition or case where m is greater than n. You can take n greater than n also. Okay, no problem. Okay. So we will take the condition where m is greater than n. So in Sm, this is the Sn. So Sm will be sum of first m terms, okay, of the series. This implies, okay, so this implies for every epsilon greater than 0, this happens if only for any epsilon greater than 0, there is the natural number m such that m and n greater or equal to m implies the difference between Sm and Sm less than epsilon. So we will put value of Sm. So Sm is nothing but the sum of first m terms of the series, and m is greater than n. So Sm will be x1 plus x2 up to 7. There will be xm because m is greater than m. Then xm plus 1 up to xm. This is the Sm. Okay, minus Sm. So I will write here because there is no space. Okay, so this mod of this is nothing but our this is Sm minus Sm. Okay, so what is our Sm? Sm is sum of first n terms of the series. So x1 goes up to xn. So x1 plus x2 up to xn. Okay. Mod is less than epsilon. So difference between Sm and Sn is less than epsilon. Now see here the first n term, sum of first n term is same as this. So if you take difference, this addition of n terms and this addition of n terms will get cancelled. This happens if you only difference. Now what is the difference now? Xn plus 1. Next will be xn plus 2 up to xm is less than epsilon. Okay. So this is the Cauchy convergence criteria for the series. Okay. So mod of xn plus 1 plus xn plus 2 up to xn is less than epsilon. Okay. So this is the Cauchy convergence criteria. Okay. Now in sequences we have seen algebra of limit of sequences. In that point we have seen if two sequences are there x and y with limit x and y, then xn plus y1 converges to x plus y, xn minus y1 converges to x minus y, xn into y converges to x into y, and xn upon y converges to x upon y, where y is not equal to 0. But in the series, okay, in the series only 2 points out of these 4 points is current here. Okay, the other 2 points are not valid. Which are they? We will see. Okay, now in the series, if there are 2 series xn and yn. Okay, there are 2 series xn and series yn, such that series xn is convergent and its sum is x. What is the sum of series? Is the limit of the sequence of partial sum. Okay, suppose series xn and yn are convergent series with limits or with sums x and y respectively. Okay, x and y respectively. Then the series xn plus y is also convergent and its sum is x plus y, which is also true. Okay, probably very simple. Okay, so it is the homework for you. Okay, you don't need to do any hard thing in proving that the sum of the series is convergent to x plus y. Also, the difference, the series x minus y is also convergent and converges to x minus y. But now, in the sequence, if x and y were 2 sequences, then x into y also convergent and converges to their product of limits. But here, in series, if x and y are 2 series, then it is not necessary that the series xn into yn, that the series xn into yn, it did not be convergent. Okay, though the series x and y are convergent, the product of these two, the product of the series of product xn into yn did not be convergent. Okay, you will see the example. Okay, for this, that this series is not convergent. Although the series xn and series y convergent, the series xn into y is not convergent. Okay, so let's take an example. So let's take xn is equal to minus 1 raised to power n upon root n. Okay, or take simple example. Just take xn is equal to, okay, xn is equal to 1 by root n. Okay, and take yn is equal to also 1 by root n. Okay, so xn is series xn is the series whose n term is 1 by root n, and yn is the series whose n term is root 1 by n. So both series are same. Okay, this is the series 1 by root n, this is also series 1 by root n. Now n term is here 1 by root n, here n term is 1 by root n. So series xn into yn now will become series. What is xn? 1 by root n. What is yn? 1 by root n. So 1 by root n into 1 by root n is equal to 1 by n. So series xn into yn is series 1 by n. But we have seen the series 1 by n is not convergent. Okay? Because we have seen the sequence of partial sum for this series. The sequence of partial sum for this series is 1 plus 1 by 2 up to 1 by n, and this sequence is not convergent because this is not a Cauchy sequence. So here, although the sequence x and y were convergent, the series x into y were not convergent. Okay, this is the example. Yes, the series x 1 by n is not convergent because sequence of partial sum 1 by 1 is 1 plus 1 by 2 up to 1 by n is not Cauchy sequence. So this sequence is not convergent. The sequence of partial sum is not convergent, so the series is not convergent. Okay. Now the next point is the series of non-negative term. Okay. So in this topic, you will see the series of non-negative terms means the series in which each term in that summation is always positive or greater equal to 0. It is not negative. Okay. So definition is the series xn is said to be series of non-negative terms. Okay. The series xn is said to be series of non-negative terms if and only if xn is greater than equal to 0 for all. That is, each term x1, x2, x3 up to so on, each term is greater than equal to 0. Okay, so there is no term in that summation which is negative. Okay. So this is called series of non-negative terms. So we will point out one observation for series of non-negative terms. Okay. So let xn be let series xn be non-negative. Okay, series of non-negative terms. So let xn be the series of non-negative terms. Okay. So this implies for this series there is a sequence of partial sum, say Sn. So let Sn is equal to sum of first n terms x1 plus x2 up to xn. Okay, this is the sequence of partial sum for this series. Okay, this is the sequence of partial sum. Okay, for this series. Now this is Sn. The sequence of partial sum whose n term is this. We will also calculate Sn plus 1, n plus 1 term, n plus 1 term of the sequence of partial sum. And what is this? This is equal to x1 plus x2 up to xn plus 1. Now, if we take difference between Sn plus 1 and Sn, what will we get? Now see, in Sn plus 1, what is the x1 plus x2 up to xn? This is nothing but Sn. All terms are here. So if we subtract Sn from Sn plus 1, the only term remaining is xn plus 1. And this is equal to xn plus 1. And this is the series of non-negative term. So each term in the summation is greater equal to 0. This xn plus 1 also greater equal to 0. That is, the difference Sn plus 1, difference between Sn plus 1 and Sn is greater equal to the 0. That is, Sn plus 1 minus Sn is greater equal to 0. This implies Sn plus 1 is always greater equal to Sn for all them. And what is this? Sn plus 1 is greater equal to Sn. This means this sequence of partial sum is monotonic increasing. This next term is always greater equal to previous term. This implies the sequence Sm of partial sum is monotonic increasing, and we know that the sequence which is monotonic increasing is convergent if it is bounded. Okay, so we come to the point, the if series is series of non-negative terms. Okay, then to prove a series is convergent, we have to prove just that the sequence of partial sum for this series is bounded. So I will repeat. Suppose we are given a series of non-negative terms and we have to prove that this series is convergent. Okay, then what we will do? We will find sequence of partial sum and we will prove that sequence of partial sum is convergent. So series is convergent. But in case of series of partial sum, in case of series of non-negative terms, the sequence of partial sum is always monotonic increasing. So if we prove, so if we show that Sn is bounded, then what we will get? Then this implies the sequence of partial sum will become convergent. Will be convergent. Okay, because the sequence of partial sum is always monotonic increasing for the series of non-negative term. So if we show directly that the sequence of partial sum is bounded, then we will directly conclude that the series of non-negative term is always convergent if the sequence of partial sum for that series is bounded. So we will calculate the correct XL. Okay, this is the series of non-negative term. Okay, so write in bracket XL is greater or equal to 0. So series of non-negative term is convergent if and only, write that if the sequence of partial sum Sn is bounded. Okay. In general, we know series is convergent if only sequence of partial sum is convergent. But here, in case of series of non-negative term, we just have to prove the series is convergent if the sequence of partial sum is just bounded. Because if sequence of partial sum is bounded, it is already bounded increasing. So it is nothing but this becomes convergent, and it will become convergent. So we don't have to worry about convergence of the sequence of partial sum because it already monoton increasing. So we just have to prove it is bounded. Okay. So this is the important criteria in case of series of non-negative term. The next point is some special series. Okay. So the first special series is geometric series. Okay. We have seen in somewhere the geometric series. Okay. So series of the form series n is equal to summation n is equal to 1 to infinity x to the power n minus 1, which is nothing but equal to 1 plus x square up to x to the power n minus 1 up to so on. This type of series are called geometric series with common ratio x. If you take the ratio of any two conjugate terms, okay, so x2 upon x1, second term upon first term, x by 1 is x square upon x, next term x cube upon x square is equal to x. So if you take the difference between any two conjugate terms, that is next term upon previous term, you will get x. So this type of series are called geometric series with common ratio x. Okay. We will see a theorem related to geometric series. The theorem says a geometric series x to the power n minus 1 is convergent to 1 upon 1 minus x whenever x lies between 0 and 1. Okay, and diverges for x greater or equal to 1. That is, this series says this series is convergent if the x is always less than 1. If x lies between 0 to 1, then only this series is convergent. And this series converges to 1 upon 1 minus x when x lies between 0 to 1. Otherwise, whenever x greater or equal to 1, series is divergent. Okay? So we will prove this. So we have given geometric series. Okay. So we have given a series, geometric series, x to the power n minus 1, n minus from 1 to infinity. Okay, so this is the geometric series, the common ratio x. Now the n term of the series, the n term of this series is n term of this series is x raised to the power n minus 1. Okay? But because the first term is 1, second term is x raised to the power 1, third term is x raised to the power 2, so n term will be x raised to the power n minus 1, not x raised to the power n. Okay? So n term of this series is x raised to the power n minus 1. Okay, so now what is the sequence of partial sum for this series? The sequence of partial sum is nothing but the n term of this sequence will be sum of first n elements or terms of this series. So sequence of partial sum Sn is equal to 1 plus x plus x square up to x raised to the power n minus 1. Okay. Now first we have to note that since this is a geometric series and the value of x is always greater or equal to 0, is a series of non-negative terms. So we know to prove the series of non-negative terms is convergent, we just have to prove the sequence of partial sum is bounded because it already is more by increasing. Okay? Yes. So this is the sequence of partial sum for the geometric series. Okay. Now we know the formula for this 1 plus x up to x raised to the power n minus 1. This implies, okay, so this implies Sn is equal to, we know the formula. What is the formula? This sum is equal to 1 minus x raised to the power n upon 1 minus x. Okay, for x greater than 0, or we can take 3 cases here also. Okay, so this Sn is equal to this whenever x is strictly greater than 0. Okay, and less than 1. Okay, now for x greater than 1, this will be equal to again same, but we can write this as, we can take minus and common here and minus find common here also. So this will be equal to, this will also write x raised to the power n minus 1 upon x minus 1. But these two are same. Okay? So we can write this is the value for x greater than 1, and for x equal to 1, what is the value of Sn? Put x is equal to 1 here. 1, 1, 1. So 1 plus 1 plus 1 or n times, so this will be equal to n. So it is equal to n for x is equal to 1. Okay. This is our Sn. Okay. So Sn is equal to this. Okay. Now we will find the limit of Sn as n tends to infinity. But before that, we know the limit of x raised to the power n as n tends to infinity is equal to 0 if 0 is less than x less than 1, and the limit is equal to infinity if x is greater than 1. We know the limit of x raised to the power n. Okay, as n tends to infinity, if x lies between 0 to 1, limit is 0, and if x is greater than 1, limit is infinity. So using this, the limit of Sn is equal to, so limit, so for 0 less than x less than 1, limit of Sn is equal to limit of this. So limit of 1 is 1, limit of x raised to the power n, when x lies between 0 to 1 is 0, so 1 minus 0 upon 1 minus x. Here there is no n, so this is as it is. So limit of Sn will be equal to 1 minus limit of x raised to the power n, but it is equal to 0 if 0 is less than x less than 1. So 1 minus 0, that is 1 upon 1 minus x as it is. Okay. Now whenever x greater than 1, the limit of Sn as n tends to infinity. But when x greater than 1, limit of x raised to the power n is infinity. So limit of this x raised to 1 is infinity because x greater than 1, so infinity upon x minus 1. This 1 is some real number, x is some real number, 1 is some real number, but the numerator there is infinity, so the whole term stays to infinity. So when x greater than 1, limit of n term is infinity. Okay, and when x is equal to 1, the sequence is n. Again, for x is equal to 1, limit of Sn as n tends to infinity is equal to limit of what is Sn? This is n. So Sn is equal to n for x is equal to 1. So limit of Sn nothing but limit of n as n tends to infinity. So this limit is equal to infinity. So from this we can say whenever 0 is less than x less than 1, the limit of Sn is exist and bounded, and it is equal to 1 upon 1 minus x, because x is greater than 0 and still less than 1. This term is defined some finite number. Okay, so we can say that this our sequence Sn of partial sum is bounded only when 0 is less than x less than 1, otherwise it is unbounded. Okay, so sequence from this we can say the sequence Sn of partial sum is bounded when x lies between 0 to 1 and limit exists equal to 1 upon 1 minus x. This implies the geometric series is convergence for 0 is x less than x less than 1 and converges to 1 upon 1 minus x. So this Sn is sequence of partial sum is bounded for only x lies between 0 to 1 and the limit of Sn is equal to 1 upon 1 minus x for 0 less than x less than 1. That is, the geometric series is converges to 1 upon 1 minus x for 0 less than x less than 1. Otherwise, when x greater than 1 and for x is equal to 1, that is, for x greater than or equal to 1, Sn diverges. Okay, so from this we can say the sequence of partial sum is convergent in this interval x lies between 0 to 1. This implies the series of the geometric series, the series corresponding to this sequence of partial sum is this series is convergent to 1 upon 1 minus x for x lies between 0 to 1, and for x greater than or equal to 1 it is divergent. Okay, this is the first special sequence known as special series known as geometrical series. Okay, and geometric series is convergent only for x lies between 0 to 1 and converges to 1 upon 1 minus x, otherwise it is divergent. Okay, for x greater or equal to 1. We will see one example. The example is test the convergence of the series. Okay, is the convergence of the series whose n term is 1 upon 3 raised to power n. Okay, so here this series we can also write it as series 1 by 3 raised to power n. Okay, they are same because 1 raised to power n is 1 upon 3 raised to power n. So this series is equal to, put here now here summation and limits are not given. This means the summation form n is equal to 1 to infinity. Put n is equal to 1, we will get 1 upon 3 raised to power 1. So 1 upon 3. Put n is equal to 2. So 1 upon 3 square. Put n is equal to 3. So 1 upon 3 cube up to so. This is this series. Okay. Now we will take 1 by 3 common. So this is equal to 1 by 3. So here remains only 1. So 1 by 3 is taken common, and here is 1 by 3 square. So here we are right 1 by 3. So 1 by 3 1 by 3 1 by 3 square. Then 1 upon here was 3 cube, but 1 by 3 already taken common. So 1 by 3 square up to so on. At some point it will be 1 upon 3 raised to power n minus 1, because here sometimes 1 upon 3 raised to power here up to so on up to so on. Okay. Now see the bracket 1, this 1 by 3 square plus 1 upon 3 raised to n minus 1 up to so on. This is nothing but the geometric series 1 plus x square up to 1 up plus x to the power n minus 1. And what is x? X is 1 by 3. Common ratio is 1 by 3. Take the ratio 1 by 3 upon 1, 1 by 3, 1 by 3 square upon 1 by 3, 1 by 3. 1 by 3 square we can also write it as 1 upon 3 whole square. This we can write as 1 upon 3 raised to 1 n minus 1. Okay. So this is nothing but the geometric series with common ratio. So the bracket nothing but the geometric series. Okay. Geometric series with common ratio 1 by 3. Okay, this is 1 by 3. So this series is now we have seen the theorem. Geometric series x to the power n is convergent if x lies between 0 and 1. And this here the value of x is 1 by 3. 1 by 3 lies between 0 and 1. So this series is convergent. Its sum is equal to is 1 by 3. As it is we just seen the series geometric series x to the power n minus 1 is convergent if x lies between 0 to 1. And here x is 1 by 3, which is less than 1 and greater than 0. And so the series converges to 1 upon 1 minus x. Okay. And this here 1 by 3 as it is. This sum is equal to 1 upon 1 minus x, and x is 1 by 3. This is equal to 1 by 3 as it is. So 1 upon this 3 into 1, 3 minus 1, 2. So 2 by 3. 3 and 3 get cancelled. So this is equal to 1 by 2. So this series is convergent. This sum is equal to 1 by 2. That is series 1 by 3 n is equal to this sum of the series is equal to 1 by 2. This is the use of theorem that based on geometric series. Now the next special series is P series. Okay. P series. Okay, the series of the form 1 upon n raised to the power p are called P series. And the P series test is the P series 1 upon n raised to the power p is convergent if p is strictly greater than 1. That is p greater equal to strictly greater than 1. So p may 2, 2.5 or only any one. Okay. And divergent if p less equal 1. Okay. Again, this is the series of non-negative term. If p is strictly greater than 1, then this series 1 upon n raised to the power p is convergent. And if p less equal 1, the series is divergent. Okay. We know one example. We know the series 1 by m. We already proved that series is divergent. And this series is called harmonic series. Okay. Here we can prove using P series test also. Here the value of p is 1 because 1 upon n raised to the power 1. 1 upon n raised to the power p. The value of p is 1. And the series are divergent for p less equal 1. Okay. So since the series is divergent for p is equal to 1 and p also less than 1. Here p is equal to 1. So this series is divergent. Okay. Because the value of p is 1. And the series, such a series 1 upon n raised to the power p are divergent for p less equal to 1. And we also prove this series is divergent using other methods. Okay. Now, the series 1 by root n. Okay. Now here n term is 1 by root n, which can be written as 1 upon n raised to the power 1 by 2. So this series is nothing but series 1 upon n raised to the power 1 by 2. Here value of p is here p is equal to half, which is less than 1. And we know the p series 1 upon n raised to the power p are divergent for p less equal 1. And this p 1 by 2 is less than 1. Okay. This implies this series is divergent by p series 2. The series 1 by n cube, that is equal to 1 by 1 cube. So 1 upon 2 cube, 1 upon 3 cube. Okay. Now this is again p series with p is equal to 3 and 3 is greater than 1. So here p is equal to 3 Okay, which is greater than 1, this series is convergent and these are divergent. Okay, by using P series test. Okay, understand the P series test.